Okay guys, let's finish this course off. So we're almost there. We just have one more complexity class, set of languages, kind of a distinction between languages, classification to get through. What am I talking about? Well, we've seen P, we've seen NP, we've seen NP complete, we just saw NP hard, and the last one we're going to look at in this course is something called co-NP. Co-NP. What does that mean? Well, in order to understand what co-NP is, let's take another look at what NP is and maybe refresh ourselves on some of those formal definitions of NP. Remember we had like that polynomial time verifier stuff going on. It looked kind of crazy. We had those like certificate strings or witnesses. We'll get back to that in just a moment. Look at that one, and from there hopefully we'll be able to kind of get a stronger grasp of what co-NP might be. So we've seen this language before. This language VC, it's the vertex cover problem. I'm going to say this is the encoding of all graphs G and K, some number K, such that there exists a vertex cover C, we'll say. And I'm not going to write it, but when I say there exists a vertex cover C, I mean a vertex cover C of G, such that the magnitude of C is less than or equal to K. So we've seen the vertex cover problem, and we've shown that it's NP complete, and we've shown that it's in NP, but let's just take a refresh here, take a little bit of a review and try to understand, well, why is it in NP again? How do we know that? How can we verify it? What can we verify? And maybe what can we not verify? Okay, so let me hit you up with something. What if I have some graph and some K, and it just so happens, you might not know this ahead of time, but I'm telling you right now, that this in fact is an element of the vertex cover problem. Well, how would we ensure that? Does there exist some certificate C, some witness C? Remember, that's what we called it before. Really, it's just a solution. But does there exist some other string that we can supply to a polynomial time verifier that we can conclude then that yes, this is in fact in vertex cover? Well, think about it. What do I need to supply to that polynomial time verifier? Well, if I supply a correct solution, and if GK is in fact an element of vertex cover, that means there does exist a vertex cover, remember, that has magnitude less than or equal to K. Well, I just supply my verifier, I'll call it V, give V, that's my verifier for the vertex cover, maybe I'll even give it a little subscript, VC, I give it G, I give it K, and I give it C, where C here, the witness, or the certificate, depending on what textbook you're reading, is a vertex cover, solution. It in fact would be a vertex cover of size less than or equal to K. So I supply it with that solution, and you say, oh, okay, it checks, makes sure it's a valid solution, but if GK is an element of VC, I know such a valid solution exists, so I know this C exists. Might be hard to determine that C, but I know it exists theoretically, and I can supply my verifier, my polynomial time verifier, with it, and it's going to be able to check in polynomial time, okay, yes, this this GK is definitely an element of VC. So if this, it's an encoding, it's a string, if this string is in this language, or if this graph and number is in this problem, same thing, then yes, there exists some other piece of information, a certificate or a witness that can supply to my verifier so it can verify it in polynomial time. Well, what if we look at the other case? So this is case 1. What about case 2 here? What if I have a G and a K that's not an element of the vertex cover problem? So if GK is not an element of the vertex cover problem, is there a string I can give my verifier that can determine, okay, or verify, rather, yes, this is not an element of VC in polynomial time. Well, let's think about that. So maybe I give my verifier some C. Maybe C is not a vertex cover. C, maybe 1, not a vertex cover. Maybe a second case is a vertex cover but has size greater than K. So if GK is not an element of VC, well then there definitely exists, covers of this graph that aren't a vertex cover of size K or less. So yeah, I can first off give it something that's completely not a vertex cover. And I can give it a vertex cover that has size greater than K. But just because I'm supplying my verifier with these things, does that guarantee that GK is not an element of VC? It doesn't, because I could do the exact same thing up here. I could just give it some bogus vertex cover, or give it a vertex cover of greater than K, and it doesn't give me any new information. Just because the solution you gave me isn't a valid solution doesn't mean a valid solution doesn't exist. So supplying me with an incorrect solution or potentially a completely invalid solution doesn't give me any new information. So what's the bottom line here? Well, if GK is an element of the vertex cover problem, then I can verify it in polynomial time. If it isn't an element of the vertex cover problem, I can't necessarily verify it in polynomial time. So in other words, the yes answers to this decision problem, where yes answer is yes, there is a vertex cover of size K or less in this graph, I can verify yes answers in polynomial time. I might not necessarily be able to verify no answers in polynomial time. Well, that's a distinction. I can determine if something's an element if it is in polynomial time, verify it in polynomial time, but if it isn't, I can't necessarily verify it in polynomial time. I can always check a solution in polynomial time, but I can only verify, or there only exists, correct solutions to verify things in polynomial time here, not necessarily down here. Well, let's look at a different language. Let's look at the complement of the vertex cover problem. What would that look like exactly? Well, there's some fine print, but I'm going to define it like this. So we take in a G and a K, and I basically negate this statement here. So I say, okay, for all vertex covers C, what's true? Well, I'm just negating it. I negate the there exists, becomes a for all, and I negate the subject here. So that means the cardinality of that vertex cover C is greater than or equal to K. Okay. So now let's consider the flip of this. Now let's consider an instance where we'll take a look at this one first. It isn't in VC complement. So imagine that. So I give you a graph and a K, and consider the case where it's not an element of VC complement. And just to review what VC complement is saying is, look, for all vertex covers of this graph G, those vertex covers have size greater than K. There does not exist a vertex cover that's size K or less in G. Okay, so what am I saying if I'm saying GK is not in VC complement? Well, if I'm saying that, I'm essentially negating this, which kind of looks like something over here. But essentially what I'm saying is, look, in G, there does exist at least one vertex cover of size less than K. Okay, so can I verify, does there exist a solution or another piece of information, again that witness or certificate, that can supply a verifier to tell me, yes, in fact, GK is not an element of VC complement. So we give our verifier, I'll call this, kind of put that complement on the wrong part there. Call this one verifier for VC complement. I give this of course, the graph, K, and I supply it with that certificate. And that certificate, what's it going to be? It's going to be a vertex cover, very similar to over here, of size K or less. And remember, if GK is not an element of VC bar, then that solution, that C, has to exist. There has to be a vertex cover of size K or less, otherwise it'd be in VC bar. So that exists, and I can verify it in polynomial time. Okay. Well, what about the flip side? We have the flip side down here. So this is case 1, case 2, and you guys probably already see where I'm going with this. But what if GK is an element of VC bar? Well, so this doesn't work. And we see a similar story over on this side. Is there any certificate or other piece of information that I could supply to my verifier so it could say, yes, for sure, this GK is definitely an element of VC complement? Well, in order for it to be an element of VC complement, we're saying all vertex covers of G have to have size greater than K. So what piece of information can I supply to convince this verifier that that's the case? Well, if I give it a vertex cover that has size greater than K, and I say, okay, well, good, I know there exists a vertex cover of size greater than K, but I'm trying to figure out if all vertex covers have size strictly greater than K. And just because you gave me one where it is greater than K doesn't mean they're all going to have something greater than K, have cardinality greater than K. So it boils down to the exact same problem as over here, but we cannot verify this. Well, I shouldn't say we cannot, we probably, maybe I should say, or at least we don't know how to verify this yet, if we can. In polynomial time, that is. Okay, so it seems like when we, over here, we can verify in polynomial time the yes answers, but we can't necessarily verify in polynomial time the no answers. So if the string is an element of this language, then we can verify in polynomial time given another piece of information, or the other piece of information is the solution in this case. In general, it's something like certificate, witness, whatever. But we can't necessarily verify the no answer. So given the string, if it's not an element of that language, we can't verify that necessarily in polynomial time given an extra piece of information. We can verify yes answers in polynomial time, not necessarily no answers in polynomial time. Well, over here, it's like the flip side of that story. So when we take the complement of this language, we can verify in polynomial time the no answers. If a string is not an element of this language, we can verify in polynomial time, okay, yes, this isn't an element of this language. However, we cannot necessarily verify in polynomial time the yes answers. So if this string is an element of VC bar, we can't verify that in polynomial time necessarily. Okay, so it seems like when we take the complement, things kind of get mirrored over here and they're related, but you know, based off this definition, we can't really say that VC is in NP, VC bar. Sorry, we definitely know VC is in NP, but we can't say that VC bar is in NP. Why? Well, in order for something to be in NP, you go back to your definitions. If it is a string, then yes answers have to be able to be verified in polynomial time. Over here, we can't necessarily do that. Or maybe we can, maybe we just haven't figured it out yet, but we don't know how to do it right now. So if it's not in NP, what's it in? Yeah, you guys, if you were following along, shouldn't be too much of a shock that there is another set that we can put it in. And what does that set happen to be? Co-NP. So what's co-NP? Well, we say A is an element of, well, you know what? I'll call it NP if and only if A bar is an element of co-NP. So how do you define co-NP? Well, you just take all the problems in NP, complement them, and there you have it. And I don't want to say a lot about co-NP, but I'll hit you with a couple things that might be intuitive for you, maybe not, but you can always, you definitely have the knowledge to check them on your own. So we know that P is a subset of NP. It also holds from a very similar proof or argument that P is also a subset of co-NP. So what's the big open problem right now in computer science? And definitely, you might say, hey, it's not really all computer science. I'd probably say it is, but definitely the biggest open problem in this material is, does P equal NP? Well, there's another open problem in this material as well. And that's, does NP equal co-NP? We don't know. But what we do know is this. If NP does not equal co-NP, this implies P does not equal NP. Or if you take the contrapositive, if P equals NP, that implies NP equals co-NP. So I'm going to leave this as an exercise for you guys. Try it out. It's not too bad at all. But I mean, these questions are beyond the scope of this course to answer. I mean, the scope of this course is really just understanding what these problems are. But you should be able to prove these things pretty easily. Just think about this. If P equals NP, what has to be true? Well, that would imply that NP equals co-NP. You just give it, play around with some of the definitions, play around with this verifying stuff, and play around with what you know about P. So that's really all I want to say about co-NP. At the end of the day, you take all the NP problems, the classic ones, vertex cover, 3-sat, knapsack, subset sum, negate it, that's in co-NP. So, or take the complement of it instead of negate it, however you want to say it. Take the complement, that thing's in co-NP. And if you're in co-NP, you can verify the no answers in polynomial time. You can't necessarily verify the yes answers in polynomial time. So I don't know how long I've been up here, but we can call an end to this course to an end here. So hopefully you learned something. I know it's not everyone's favorite course. A lot of people have to take it. I tried to make it as accessible as possible. Just be ready for the exam. All the information is on Piazza right now, and we can, of course, discuss on Piazza a little bit more the exam and the material to come there. Usually, I will say this, usually at the end of the course, I open up the floor to basically like an AMA. So you can ask me anything about the exam, anything about the course material, and once we run out of those questions, ask me anything in general. Well, of course, we can't do that right now because you're not here. However, I think I will open up a thread on Piazza where it'll be like a general AMA, and I'll, of course, give priority to the exam questions and the material questions of the course. However, if you want to ask me a general question, go for it. I do warn students, however, I might not answer every question you ask. And remember, on Piazza, you might be anonymous to your colleagues. You are not anonymous to me. So I'll be posting that up pretty soon. Otherwise, thank you very much for your attention, and good luck on the final exam.